Good evening, everyone, and welcome to this special lecture that's going to be given by Professor Andrea Macciò. Professor Macciò's research interests revolve around unveiling the nature of dark matter using state-of-the-art computational technologies to simulate the way galaxies form and evolve. Here at NYU Abu Dhabi, he directs a group of 3 postdocs, 3 PhD students, and several undergrad students. He is an author of 140 research papers that have accumulated more than 10,000 citations. In 2019, he was one of the recipients of the 10-year Golden Visa for Scientific Merits from the UAE government. Andrea joined NYUAD in 2015 from the Max Planck Institute for Astronomy in Heidelberg. He is currently Associate Professor of Physics and Director of the Center for Astro, Particle, and Planetary Physics, CAP3. In today's talk, Andrea will lead us on an exciting trip from the very first spark of our universe to the current structure, a story that is full of twists and mysterious dark characters. Thank you.
Thank you, Marta, for the very nice introduction and for not mentioning my golfing and fencing skills that Francesco suggested. Welcome, everyone. I'm very glad to have you here and finally to give a presentation in person. I think it's 2.5 years I'm not talking in front of a public, so I feel a little bit of pressure. Okay, the title of this seminar is A Brief History of the Universe, which is an homage to a book which is called A Brief History of Time, written by Stephen Hawking in the 80s. When I read that book, I think I was around 15, and I think I understood, 40% of it. But I decided that the subject was so nice, so cool, that I needed to learn more, and that's how I am here in front of you today, since I've spent the rest of my life trying to understand more about the universe. Full disclosure, I haven't read the book again since I was 15, because I'm so scared that I only understand 40%, that I leave the book on the shelf, and maybe one day I will pick it up. Could be my retirement plan. Okay, a brief history of the universe. This one is a nice picture of our night sky, and the human beings have always been fascinated by the night sky. This is a picture that's done here in the Abu Dhabi desert, near to a line, with a nice camera. Now, if you have a better camera, let's say the Hubble Space Telescope, you can take a picture like this. Okay, this is a picture again of the night sky, slightly higher resolution, and it shows you what the sky is made of. And now, if you remove some of those very bright objects, those are nearby stars, what you see here is just galaxies. Okay? There is a sea of galaxies in our universe, and so the history of our universe is the history of the formation of galaxies. So what I will do today, I will take you through a journey and try to understand how the universe formed through galaxies. Before doing that, I need to prepare you to just few technical details. I'm sure you're all familiar with that, but I will go through that anyway. In astrophysics, we deal with gigantic numbers. Okay? Everything is billions of trillions of billions. And so what we have to do, instead of writing those numbers down like this, right? That's 100 billion galaxies. That's the number of galaxies we think is in the universe. So it's a 1 followed by, so for 100 billions, it's 11 zeros. So instead of doing this, I'm going to use exponential notation. So that means I'm going to write this number as 10 to 11. Okay, 10 to 11 means it's a 1 followed by 11 zeros. And we're going to have very big numbers, 10 to the 24, 10 to the 40. So that's why I need to use this notation. This notation works both ways. You can also use it to express numbers that are extremely low. For example, if you have to write 0,00001, you can write it as 10 to the minus 5. So the minus in front of the exponent simply tells you that the zeros are after the comma. Okay? So 10 to 11, big number, 10 to the minus 5, a small number. Galaxies. Galaxies comes in a very large variety of form and dimensions. This is an example of 2 spiral galaxies. Those are also pictured from the Hubble Space Telescope. And this galaxy here is very similar to our own galaxy. We live inside our own galaxy, so we cannot take a nice picture of it, right? It's like you try to take a picture of your house while you sit in the living room. You cannot do it. You have to go outside and take the picture. We cannot travel outside our galaxy, so I don't have a nice picture of our galaxy. But we think that the Milky Way, it's a spiral galaxy, and the sun's going to live about here on one of the spiral arms. But galaxies also come in different shapes. For example, those are spherical galaxies. And the history of the cosmos is the history of the galaxy. So let's try to see how the universe evolves. And now we are facing another issue. We are facing the issue of big numbers in time. So the universe is 13.7 billion years old. That means 13.7 10 to the 9 years. And again, if I'm going to tell you after 400 million years, after 500 million years, it's very hard to understand. Is that a lot of time? Is that a little time? So what I will do in this lecture, I will use an idea from Carl Sagan, that's not my idea, it's his, and rescale the length of the whole life of the universe to 1 year. What does it mean? It means that the Big Bang is happening at the midnight of January 1st. Okay? And today, it's the last second of December 31st. Okay, so we're going to go from January 1st to December 31st. So instead of telling you after 3 billion years, I will tell you in March. What does it mean March? Well, March is the third month of the year, so it's roughly 1/4 of the life of the universe. Okay? Now, what we will see is that in this beautiful scale, I will use practically the first 10 days of January and the last part in December, okay? Because the universe evolves in a very strange way. But that's our idea. We're going to use this as a time scale, which I think is going to be useful to guide us through the cosmos. Okay, let's begin. The Big Bang has happened. We are right after the midnight. And what do we have in the universe? Well, we are all familiar with the matter that lives around us, and so I think you already have seen the concept of protons and electrons. Protons are positive particles, very massive, and the electrons are negative charged particles. So that's what we have at the beginning. It's a sea of protons and electrons. Now, protons and electrons, what they want to do, since one is positive, the other one is negative, is to get locked into atoms, right? That's a matter that we know. Problem is that they are not the only two characters in our initial history, because we have protons, we have electrons, but we have another kind of particle, which is photons. What is a photon? A photon is a particle that propagates light. So one idea when you think about light is like think about water. So water you see as a continuum, but it's made of molecules. You can think as light, as the light that's coming from the projector and blinding me at this moment, as light made of little particles, okay, like the molecules of the water. So photons are just the propagator of light, of electromagnetic radiation in general. So I say that protons and electrons, they want to meet and want to make atoms, but they have a problem. They are outnumbered by photons. So how many photons do we have? For every couple proton electron, we have 1 billion 10 to the 9 photons. What does it mean? It means that those two poor guys that really want to go to each other, they are embedded in the sea of photons. Now, trying to give you an idea, that's the same as Tom, who's looking to catch Jerry, but he has to go to the whole population of China. That's 1 billion people. Okay, that tells you how difficult it is for Tom to catch Jerry, or if you want, for the proton to get the electron. Okay? But there is a but. The universe is expanding. The universe started with a Big Bang, is an explosion, as like when you throw a stone into water, you create ripples, and those ripples expand. So our universe is expanding, and while it's expanding, it's also cooling down. That's exactly the expansion of a gas cools it down. That's exactly what we use in the AC all over Abu Dhabi to cool our houses. We expand the gas, and the gas cools down. The same for the universe. The universe is cooling down. What does it mean? It means that after 15 seconds after January 1st, the electrons have lowered their temperature, and so they cannot really push anymore on the protons and the photons have lowered their temperature, so they cannot push anymore on protons and electrons. So what's going to happen is that the photons are going to fly away. Okay? So suddenly we have Tom and Jerry, and the entire population of China runs away. Okay? So finally Tom and Jerry can meet and can try to start to build atoms. So again, we are 15 seconds after January 1st, so our year just began. And so protons and electrons are going to lock itself, and they're going to form the simplest atom in the world, which is the hydrogen atom, which is the building block of all other atoms. The other thing that protons and electrons do is that sometimes they collide at such high velocity that they penetrate each other, if you wish, and they form a new particle. Proton is a plus, electron is a minus, so the new particle is going to be 0. It's a neutral particle. It's called neutron. The neutron is very important because you use it to build more complex atoms. In fact, the next guy we were going to build is the helium atom. Right? The helium atom has 2 protons, 2 red neutron, 2 neutron, 2 protons, and 2 electrons. Okay? And the photons, where do they go? Well, I told you they escape, but they can't really escape from the universe. Right? What they're going to do, they're going to go around and start to permeate the whole universe. This is a map of the galaxies in the universe, and you see that this map, it's very non-uniform. You have regions with a lot of galaxies. Each point here is a galaxy. You have a region with a lot of galaxies and other regions which are slightly empty. If I make the exact same map for the photons, boom, it's uniformly blue. Okay? Those photons, they are permeating now the universe. So those photons, they come straight from the Big Bang and now are in this room, zipping around. They are extremely cold. In fact, the temperature of the universe is only 2.735 Kelvin. You know, Kelvin is this absolute scale of temperature, so I scale here in Celsius is minus 270 Celsius. Those photons, they are all over the place, and in fact were discovered in 1965 by 2 engineers, Penzias and Wilson. What Penzias and Wilson were doing, they were building an antenna, this one, believe it or not, this object here is an antenna in the 65. And what they were doing, they were building this antenna for the Bell Laboratories, for telecommunication. And what they did, they built the antenna, they switched it on, and there was a lot of noise. And they thought, oh, we must have pointed it towards some radio station around. So they start moving the antenna. And they found exactly the same noise. And then they keep moving the antenna, and then they realized that no matter where they look at, those noise was coming exactly the same from all over the direction. And then what they did, they were smart, they were engineers, they phoned up a physicist, right? They phoned up a physicist in Princeton. And that's what an engineer does, right? I mean, when he has in trouble, calls a physicist. I'm a physicist, if in case you haven't noticed. And so they phoned up the physicist, and the physicist, which was Gamow, told them, look guys, you might have stumbled on something amazing. And in fact, what they found was exactly the relic of the Big Bang. And they were awarded the Nobel Prize in 1979 for the discovery of the cosmic microwave background. Okay, now, there are people here that have some gray area like me, so they might recognize this picture. I think for the younger ones, they have no idea what I'm showing you. That's a static that you have in a cathodic tube television. So if you're born before the 80s, you must have seen this. I can tell you that 1 in 100 of this white spot here, it's a photon from the cosmic ray background, who is hitting the cathodic tube of your television. So when we were all young and we were trying to fix our TV, what we had, what we call static or white noise, it's actually the echo of the Big Bang. Okay? Those photons that were impinging the cathodic tube television, and you were seeing them as fog. Okay, very good. So now we are 15 seconds, we built 2 atoms, and now what we have to do, we have to build the whole periodic table, right? Because we want to make, among many things, humans, this board, trees, fishes, whatever. Problem is that it's over. We are not going to form any other atoms. That's a picture of the periodic table that I'm sure you've seen. And you see the variety of elements we have on Earth. And after the Big Bang, after 15 seconds after the Big Bang, we were only able to form just the tip of the iceberg here. Just hydrogen, helium, a little bit of lithium, and a little bit of beryllium. No other elements can form. And the reason is that the universe is expanding so fast that the atoms cannot meet anymore. And when they meet, they are not fast enough to penetrate each other. So now we are left with a bit of a conundrum, right? Because we cannot form any other atoms, so where do they come from? And we'll come back to that later. Now you will see how our clock is skewed, because 15 seconds after January, and now to wait for the next event, we have to wait till February. Okay? Nothing happens till mid-February, so it's a very boring year. And finally, the first galaxies and the first stars are start to build. Okay, so now our atoms, they start to get together, and when they get together, they provide a lot of gravity, and this is going to create the first galaxies and the first stars. Okay, now let's suppose that you are like me, you are 17 years old, and you really want to understand the formation of galaxies. How do you do that? Okay, how do you understand the formation of galaxies? Well, technically, there's a very simple way to do that. And this has been brought us more than 500 years ago by Galileo Galilei. Galileo Galilei told us that if you want to test a theory, you must use the scientific method. What does it mean? It means that you need to create a theory, you need to devise an experiment, and then you're going to test your theory. Well, that's very easy if you want to study, as Galileo did, how objects fall from the Pisa Tower. Now, if you want to build a galaxy, you have a bit of a problem, right? How do you build a galaxy in a lab? Right? Galaxies involve temperatures, densities, timescales, which are far beyond what we can do in the lab. So how can you apply the scientific method to galaxies? Well, the answer is that we can use computer simulations. Okay? So what we try to do is to create a galaxy in a computer and then go and check if what we do, well, the final product of our simulation is similar to the galaxies we see in the sky. If the answer is yes, then we are good because our theory checks out. If the answer is no, we're going to change the game. Okay, now it seems I've changed one problem with another problem, right? How do you create a galaxy in a computer? Okay, how do you tell a computer, please, can you make a galaxy? Alexa, can you make a galaxy? Nothing is happening. So, but I try to convince you that creating a galaxy in a computer is very easy. And I always tell my students, if I do it, it must be easy, right? I don't do complicated stuff. And so I'm going to try to convince you that creating a galaxy is not different from baking a cake. Okay? As silly as it sounds. So now we're going to use this beautiful flipboard, which was scaring our friends from the video because they think I'm going to write very small. Okay, now, I think the majority of the people in this room have baked a cake in their life, so what do you need to start? You wake up. Very good. So we have eggs, flour. Okay, very good. So what does it mean that we need? We need ingredients. That sounds lovely. So if we want to make a cake, you need the ingredients. Okay, there we have the ingredients. Now, what are the ingredients of a galaxy then? I'm not going to do all the work, right? Come on. Okay, whoa, one at a time. I heard stars. Moon, planets, gas, asteroids, I heard dust. That's very advanced. Comets. Can I put comets into asteroids? Okay, now, let's make a comparison. Those are the ingredients that you told me, right? Those are the ingredients you gave me for the cake, like I have egg. Okay. Now, nobody told me as ingredients for the cake, frosting. Why did anyone say frosting for the ingredients of a cake? It's unhealthy, that's a good one. It's frosting an ingredient. Well, if you have eggs, flour, milk, butter, sugar, you can make frosting out of it, right? So that's why nobody say frosting, because frosting is not the main ingredient. You can make it out of the others, right? Nobody say cream, right? If you have milk, butter, you can come up with some cream, okay? So on the basis of that, let's check the stuff you put down here. So are those basic ingredients? Moon. Is the moon? No, right? I can make the moon out of the leftover of the Earth, for example. Planets, are they basic ingredient? They are made out of the leftover of the sun. Gas. Should we keep gas or should we throw away gas? We keep gas. No. Only just because it's the only thing we have, right? We only have hydrogen and helium. So if we throw away the gas, we don't go anywhere. Very good. Gas we keep. Asteroids? Now you understood the drill, right? I don't have to keep going. Dust. Stars? Aha. Okay. So you see how you've been able to set up the first step in building a galaxy. You have been able to give me the ingredients. But, there is a big but here. And the part is that there is a secret ingredient, which I haven't told you about. You might have heard about it. I think our dean spoiled it because he mentioned in the introduction. Anyway, so what is a galaxy made of? What's the secret ingredient? Well, I think it's fair to say that the secret ingredient of galaxies is the biggest unsolved mystery in modern physics. The lights are great. That's the right moment to bring them up. The biggest unsolved mystery in modern physics. I think there's nothing else that if you're a physicist, everybody should work on that, in my opinion. And what is this? Well, that goes back to a very simple problem. So I'm going to now talk about this simple problem. We have a mass m, it could be the sun, and an object that goes around of it in a circle. Okay? 1643, Isaac Newton is born, and Isaac Newton worked out that if you have a configuration like this, the object goes around with the velocity which follows this formula. I promise that's the first and only formula you're going to see through the whole talk. So make an effort and let's try to interiorize this formula. What is it telling me? It's telling me that the velocity at which, for example, the Earth goes around the sun simply depends on how far is the Earth from the sun, what's the mass of the sun, and g is the gravitational constant. Okay? Very good. Is this true? Well, I mean, Newton was following Galileo, and so we have the scientific method. And in fact, if we check the velocity of the planets, we see that Mercury is the fastest. That's our formula, right? The velocity of the planet is the mass of the sun divided by the radius. If the radius is small, velocity is large. Mercury goes around 47 kilometers per second. And then on the other extreme, we have Uranus and Neptune. And you see they go around very slowly, 5.343 seconds. Okay? And in fact, if I put them in a graph where I put the radius of the orbit versus the velocity, it goes down. Beautiful. That's telling us that Isaac Newton was right? The planets follow exactly what's called the Kepler law, which is can be derived by the Newton's law. Beautiful. Planets do what Newton say. Galaxies. Well, galaxies are disky objects, and they rotate. Okay? I think I don't have to convince you this object is rotating like this. Okay, galaxies rotate. So, since they are not different from planets and the sun, they follow the same gravity, there is the expectation that they have to follow exactly the same rule. Well, that's where things become very interesting. This is Vera Rubin in 1977. She started making observations of galaxies. What did she do? Okay, there is a galaxy here, and she's trying to build a plot of radius and velocity, how fast the galaxy goes around. Okay, so she starts by looking at something like stars that are in that where I put the cross. The light that is coming from that part of the galaxy is like this. My phone is rotating like this, right? So that means one edge is coming towards you, and another edge is receding, is going away. This generates what is called Doppler effect. If you don't know what Doppler effect is, doesn't matter. Just learn that Vera Rubin was smart enough to be able to measure the velocity of the galaxy at that point, using the fact that one part is coming towards you and one part is receding. Very good. So she started making a plot, our friend Vera, and she put there the first point. Okay, very good. Then she moves to the next point. Now, what is setting the velocity of this first point? Well, according to Newton, is the velocity is equal to the radius and the mass. But which mass? Well, I didn't tell you, but that's the mass within the radius. So you have to take all the mass within this radius. Okay, what the point is. Now you move to the next point. What happens there? What happens there is that the point is a little bit farther away. But on the other hand, this circle contains more mass, right? There's mass here, mass there, some other mass here. So this point, it's raising. Okay, so Vera keeps making observations, and everything is okay. And then she reaches the edge of the galaxy. Okay? After this point, there is nothing. Okay, the galaxy is over. But there can still be a few little stars that she can measure the velocity. She used gas, but that's a detail. And what happens that then she goes to the next point. And now, when it goes to the next point, it's farther away, more radius, but there is no new mass to put into the formula. Okay? So this point has to start to fall down. Okay? Then she goes to the next point, even lower, and keep going. Now you're very smart people, so I don't have to point one plot at a time, plot one point at a time. I can put 4 in a row, and that's what is expected. Does this look familiar? Well, the answer is yes, right? That's exactly the same we saw for the planets. When the galaxy is over, right, when there's no more mass, the points have to follow. Well, fun fact, Vera Rubin starts to make observations, and they make no sense, because that's what she finds. She finds that the rotation curve stays flat. Okay? She's moving far away from the galaxy, like going from Mercury to Venus, and the velocity is not dropping. The velocity is constant. Okay? Now, I can show you, this is a cartoon, clearly. I can show you a real plot. That's from 1885, Van Albar and collaborators. You have here the radius, the distance from the center of the galaxy, the velocity, and this is what you expect. Should go down like the planets. Mercury is faster than Venus, but that's what you observe. You see those points with arrow bars? Those are actual observations. Okay? And that's the people start scratching their heads, because now you have a problem. And so when you have a problem, you have to fight for a solution. What is the solution? Well, one solution is that our friend Isaac was wrong, Newton is wrong, and gravity works differently. That's a very hard assumption to make, right? Because we have verified gravity, so many things. In the planets, it works perfectly. Why is the galaxy different from a planet? So if you want to save Uncle Isaac and save his formula, you have to make one assumption. If the denominator is growing, and if v is staying constant, m has to grow. This one doubles, this one has to double. Remember, g is a constant, right? It's there because it's there in the formula, but doesn't play any role. Yeah, but we don't see any matter, right? What does it mean? It means that this galaxy that we see like this must have some other matter around it. Must have embedded in a ball of matter. And then what it means that when I reach the edge of the galaxy, and I'm using this mass, when I move to the next point, where I think there should be no new mass, actually there's plenty of new mass, because I have all this mass around. Okay? So, what physicists do? Now we have an idea there should be some mass around it, and that's 1985. So the only thing we have improved from 1985 to today, that we gave it a name. We call it dark matter. Okay? From a scientific point of view, we have exactly the same knowledge about dark matter as in 1985, give or take. That's how depressing it is. We have been able to say that few things are not dark matter, but that's like trying to solve a mystery, saying that, well, John didn't kill him, Joanna didn't kill him, and that's where I stand right now, right? It's not the way to go. You can't find the killer in a mystery by just excluding people, especially if you have an almost infinite possibility. So that's what we know so far. We know that this matter is dark. Why is dark? Well, it's dark because we can't see it. There's no telescope that can see it. So it must not emit electromagnetic radiation. It must not talk with protons and electrons, otherwise we will see it, will disturb them. And the only thing it does, it follows Newton's law. Okay? Very good. How much dark is a galaxy? Well, a galaxy, it's very dark. In fact, the galaxy is like an iceberg. The part we see of the galaxy is the tip of the iceberg. Most of the galaxy, we can't see it as we cannot see the rest of the iceberg. In fact, if you bring this in number, the galaxies are 85% dark. And our universe is about 80% made of dark matter. Okay? So dark matter, usually it's where students start to say, okay, how do you know? You cannot see it and you think it's there. How does it work? How can you convince me that there is something you can't see and it's there? It's like telling you my best friend, the invisible man, is here with me, right? How can I possibly convince you? Well, usually I tell them it's a kind of magic. What do I mean? I assume you must have seen some magician doing a card trick, right? More or less. So what do? They take a card, they make you sign it, right? Then they set it on fire, they destroy it, and then magically it reappears in the pocket of the guy next to you. Okay? Now you have two options. The first one is that think the guy is truly magical, right? The guy is Harry Potter. He can bend the law of physics, he can destroy a card and make it appear again. Or the second option, that I think is the one most of you think, there must be a trick. Okay? In fact, we call it magic trick. And how do you know there is a trick? Because if I ask you when did the trick happen, you can't tell me. If the magician is good, you won't be able to tell me. If I tell you how did the trick work, you can't tell me either. So how do you know there is a trick? Because you know that the law of physics cannot be bent. Okay? So dark matter is like a magic trick. We believe the law of physics. We know that the car cannot be ripped, set on fire, and reappear somewhere else. And so as we believe there is a magic trick here, we believe there must be dark matter. Because we believe in law of physics. I'm not sure if I convinced you, but that's it. Okay, dark matter, it's there, and there is plenty. In fact, if I go back to my old card, not only I know there is dark matter, but I can tell you exactly the recipes. If you want to make 100 grams of a galaxy, you need 85 grams of dark matter and 15 grams of gas. Okay? Oh, good. Now we have our beautiful ingredients. What's the next step to make the cake? If you are like me, there is something you need, otherwise you won't go anywhere. Mix? No? I can do without mix, right? But there's something I'm very bad in baking cake. So what do I need in order to bring my ingredients into a cake? That will come later, right? Because a recipe, right? At least I will start, if you start mixing ingredients at random, most likely you will end up with a 1 centimeter high, super thick dough that it's unchewable, okay? So the next thing you need is a recipe. So what's the recipe for us? Well, I hope I've convinced you that if we believe in the law of physics, the recipe are exactly the law of physics. The law of physics about, I have here general relativity, gravitation, Newton, Einstein, they're going to tell us how the elements will mix together. Okay? So I have the ingredients, I have the recipe, and I am 2 steps out of 3 towards the end. And what do I need next? Somebody said it before. An oven, right? If I want to bake, it's better if I have an oven. So what's going to be the oven for us? The oven for us is going to be a supercomputer. So what we're going to do, we're going to take our ingredients. We can teach the computer to follow the law of physics, right? Computer is very good to follow orders. And so what we have to do is take our ingredients, the law of physics, and put in a computer. Oh, by the way, this computer, it's Dalma. It's here at NYUAD and somewhere in the basement. Okay, so that's our own supercomputer. So it seems we have everything, but there is a little problem, and it's how do we prepare the dough? Okay, that seems silly, but in physics it's called initial conditions. So how do we prepare it? Do we put all the dark matter from one side, all the gas from the other? Do we mix them? Right? Do we decide to put dark matter like in a big pile, or we spread evenly on our table? And that's a question which is very important, because if you change the initial conditions, you're going to change the final outcome. And that's where our photons, our friends, come in our rescue. What happens here is that, I remember that I told you that's a blue sea of photons after the Big Bang that are here in this room zipping through us. If I look more carefully, so for example, if I look to differences in this map, I can start seeing that there are little differences. So if I start zooming in, the map has differences. And here I have very simple color code telling you that blue is cold and red is hot. So some parts of the universe, if I measure the energy of the photons, which is a temperature, is slightly hotter, and some parts are slightly colder. What does it mean slightly? The difference is super tiny. It's 1 part in 100,000, 10 to the minus 5. Remember, 0,5 zeros and a 1. Just to give you an idea, the cold is 2.7351 Kelvin, or minus 270.4149 Celsius, and the hot is minus 217.4150. It's not that you take a shower with this and not with that, right? I mean, these 2 temperatures are identical down to the 5th decimal place. So sometimes we physicists, we use very big numbers, and it's sometimes interesting to try to put them in context. So what does it mean cold and hot? Cold and hot in this case means that in some places there is a little bit more matter. That's what the hot region is. So if I think about putting down my dough, it means that I have to make little ripples. So in some places I have to put a little bit more dough of my cake, in some places a little bit less. But what's the difference between red and blue? Well, it's 1 part in 100,000. So let's do another game. Let's suppose I have the Mount Everest, right? 9,000 meters. And let's suppose I want to change its height by 1 part in 100,000, okay? The same difference. So I want to create another object, which is the Mount Everest slightly taller or slightly shorter. Let's suppose taller. What should I put on top of the Mount Everest? To change a house, I heard? Anyone else? Could be anything, a tree, a house, Burj Khalifa. An apple. It's a coffee mug. The Mount Everest is, give or take, 9,000 meters tall. So a coffee mug is 9 centimeters tall. So the difference between red and blue is the same difference in height between the Mount Everest and the Mount Everest with a coffee mug on top. Okay? It's tiny. It's tiny. It's the same difference, Mount Everest. So you can say, I'm going to climb the Mount Everest or the enhanced Mount Everest, right? So the only thing you have to do on top is like, done. Okay, so what happens to these tiny differences? That's where it becomes very interesting. It happens that this little patch of the universe has a little bit more matter than the surrounding. And so what it has a little bit more gravity. If it has a little bit more gravity, it's going to grab matter from the surroundings. And what it's going to do? It's going to grow. But now you see, right? Now this thing is even more bigger. It's even bigger. And so it's going to grab matter from even farther away. And it's going to grow. And now you understand the drill, right? This thing is even bigger, it's going to grow, and it's going to grow again. So somehow, this is capitalism at its worst, right? If you start with something more at the beginning, you're going to get richer and richer. And of course, since matter is conserved, the regions which are blue will become emptier and emptier, up to the point that the universe will go from something which is roughly uniform, right, tiny difference, to something that is not uniform at all. That's how you go from an initial dough, which is very, very uniform, differences in 1 part in 10 to the 5, to something which is very different, right? Because if you look at here, you have places with a lot of stuff and places with nothing. In fact, let's put this in context. I say that if I look at the universe at the beginning, the difference between red and blue, 10 to the minus 5. What's the difference here? For example, what's the difference in mass from a region which has a galaxy and a region next to it which has, well, I say nothing, clearly there is something, right? Some smaller galaxies, some gas. Well, the difference, now here was blue and red, here between black and yellow, the galaxies, it's 10 to the 6. So a galaxy is 1,000,000 times larger, more massive than its surrounding. What does it mean? It means that the universe is going from left to right. So it's growing from 10 to the minus 5 to 10 to the 6. This is 11 orders of magnitude. Is it a lot? Well, let's do the following experiment. Let's take an ant, and let's grow its mass by 11 orders of magnitude. What do you get? I'm not going to grade you. It's fine. Just elephant? No. Elephant, rat, too small, too small. The moon always comes out. I need to understand this thing. I mean, it's crazy. There is always someone who says the moon. Wrong. You get an Airbus A380. Actually, you get 10 of them. That's how much 11 orders of magnitude is. It's an ant that grows into the Airbus. So we've seen extremely small, Mount Everest with a cup, and extremely large. Okay. So now we're good to go. We know we have our recipe. We know how to put the initial conditions. Let's cook our universe. Okay, that's a computer simulation. So the idea is that now we are starting from this, uniformly blue, January 17th. And of course, we want to end up today, so December 31st. So that's a density map. So you see at the beginning it's uniform. And now you will see as time goes by, structure will start to appear. Okay? So this is the whole journey of the universe from January 17th to December 31st. And what you see is exactly what I was telling you. Something which is uniform is going to form structures. And structures, they form a very interesting thing. So they start as spheres because gravity is a round force. Then those spheres, they tend to be slightly squashed on some of the 3 axes, and so they're going to be squashed into pancake. Then a pancake, again, it's going to be weak on some of the axes, squashed into a filament. and then a crossing of filaments, you have the formation of galaxies. Let me play this again. You start from a uniform universe, but gravity takes over, right? Whoever is dense is going to grab more matter, and that's the way you form the universe. That's how you go from 10 to the minus 5 to 10 to the 6. That's how you transform your nth in 10 Airbuses. Okay, and now the sky is the limit, right? That's the same movie as before, just with the zoom. So I'm looking now at one particular object. This is the formation of an object that today would have the mass of the Milky Way, our own galaxy. And what you see is that these objects are broken in other objects. Okay, so what happens is that you first form little patches of matter. Those patches, they merge together, we say, they get together, and they build larger and larger objects. So you have some satellites, you have some other smaller one here, here, there, and they're all zipping around and towards the formation of the final object. Okay, this is the formation of what? This is the formation of the iceberg. That's a part which is submerged. Okay, why? Well, because I told you dark matter is 85%, right? So at the beginning, I'm going to form the 85%. Then I'm going to worry about the 15%. So what is the gas doing during that? Well, the gas, what does it see? The gas sees that the dark matter has made a ball with a lot of gravitational force, and so the gas is going to fall in. Right? There's nothing else can do. Dark matter is 5 to 1 to gas, right? So dark matter is just dragging the gas along. And the stars? Well, what happens is that if you start to pile up a lot of gas, this gas will start to feel its own gravity, and so will start to condense in a very dense object. When these objects become denser and denser, it arrives at a point that will start to ignite nuclear reaction. That's what powers the sun. Okay? So we only have gas. The gas falls into the dark matter. Then there is what is called a runaway process. So the gases keep falling, 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 and it becomes so dense. Then the atoms, they start to hit to each other. And so what happens? You start nuclear reactions. Okay? And that's how you create a star. So we are now at February 15. And finally, we have some light, right? Because remember, the initial light, the photons are gone, so the universe is completely dark. That's what's called the end of the dark age, February 15th. That's a palmarès of stars. I put here some stars to scale, just to give you an idea. And if you're wondering where the sun is the little speck there. So we live near a very, very modest star, right? I mean, we are not at the near one of the big stars. And what happens with the stars is that if they are like the sun, they're going to just run out of fuel and just fade off. But if the stars are very massive, what they do at the end of their life, they explode. Okay, those are called supernova explosions. And what you see here, it's a remnant of a supernova explosion. That's a Crab nebula. This is from the Hubble Space Telescope. The star was here in the center. It exploded. And what you see here, how it's pushed away all the gas. As every explosion that we know, its explosions are very hot. So what happens is that this gas is also very hot. So it shines a lot of energy towards us. That's why we see it. Okay? Are you still with me? Okay. Still February 15th. Huh? I hope you don't have plans for tonight. Okay. So what's happening now is that we have all the ingredients. So what we can do is finally to cook our galaxy. What you see here in these 3 panels is the formation of the dark matter. That's the iceberg. You see the gas. The gas is falling into the dark matter, and the gas is color-coded blue cold, red hot. And here you see the formation of stars. First thing you see is, as I told you, the dark matter is much more extended than the stars. You see how big is the ball of dark matter, and you see how concentrated are the stars. That's why Vera Rubin was very surprised when she saw the results. She thought that outside the stars there was nothing. Look how much mass there is outside the stars. Okay? So this movie here is the formation of Milky Way galaxy. And our own galaxy, it's formed by the end of March. Okay? So it's nice to see things more in details. So this is the formation of a galaxy which is smaller than the Milky Way. I put a time scale there, so that you see the clock here is in giga-years, but roughly 1 giga-year is 25 days in our calendar. And what you see here is what I call usually the breathing of a galaxy. You have 2 phenomena here. The gravity, what you see here is just gas, and again, cold, blue, hot, red. What you see here is that the gas is dragged to the center through gravity. So we have this process here. When it goes to the center, it makes stars. But when it makes stars, the big ones, they explode. So what we see here is that the galaxy is a continuous alternation of gas coming in and gas blown out by explosion. Okay? So when we think about galaxies, look at this very large edge here. When we think of galaxies, we think about objects that are stationary, right? Objects that have been there forever. Galaxies are extremely lively environment. So what I say here is that it's like the breathing. You see, now it's inspiring, gas is going in. Okay? What's the problem? The problem is that this breathing happens like 20 times in the life of the universe. That's why we don't see it. Okay? It takes roughly 500 million years, so 12, 15 days in our calendar for a galaxy to do one inspiration, expiration. Okay? That's why we look at stuff, we look at them as frozen in time. But galaxies are extremely lively objects. Okay, so we have formed galaxies, we have formed stars, and now we're still with a little problem, right? The periodic table. We are stuck with hydrogen and helium. So what's happening here? What is happening is that those, what we call heavy elements, fun fact, if you look at a periodic table for an astrophysicist, we only care about helium, hydrogen, and all the rest. So practically our periodic table has only 3 entries. So if I have to draw our periodic table, I think students that struggle with chemistry, as I did, will love to become astrophysicists, because our periodic table is this. Hydrogen, helium, and then we use Z for the rest. So that's our periodic table. And we really don't care. We just call them all metals somehow. Anyway, what's happening is that these heavy elements are cooked in the interior of the stars. Now, iron has 64 protons. I'm stuck on the atomic number of the iron. I told you I wasn't good in chemistry, right? I wasn't lying. So iron has 64 protons. Now, you can imagine if you want to put together 64 protons, it takes a lot of pressure, right? Protons, they all have positive charge. They don't like to stick together. So this can only happen in the center of the star. In the center of the star, there's so much pressure due to gravity that you can start cook up very heavy elements. So stars are like onions. They have iron in the center, then for example silicates, oxygen, neon, carbon, hydrogen, and helium on the exterior. But those elements are locked into the star. For example, we can't see any of those elements in the sun, because the sun is shining, but where is it shining from? It's shining from the surface. So from the sun, we only see helium. But stars explode. That means that during those explosions, those elements are released into the universe. So people usually say we are stardust, right? That's true, but that's true at a deeper level. Not only we are made of remnants of stars, but those stars had to die for us. Okay? No, I mean, if you think about the carbon in your body, and there is quite plenty, this carbon has been cooked up in some star that lived before the sun. The star has exploded. This carbon has been ejected in the universe, has been captured by the solar system, the sun, has been put on Earth, and now it's in your body. Okay? So those stars, they had to die in order to release those elements. And in fact, that's what we see in this other animation, this other scientific movie. So what we have here is the abundance of oxygen and carbon, the building blocks of life, into a galaxy. And the beginning it's blue, which means there is 0. Now, if I start the movie, what you can see is that formation starts. This is the gas. And now you see that some stars are start to form here in the center. Yeah, it's a bit bright. And those stars are forming and dying. The thing I was showing you before, like the inspiration, expiration. So when there's the expiration, the stars die, and all their oxygen and carbon is spread around. And now you see that the stars are only forming at the center, but the galaxy is able to pollute with life its whole space. Okay? So it's likely that the carbon in your body has been produced very far away from where we are right now. And you see that here, by the end of the simulation, the whole galaxy is going to be colorful, which means there's oxygen and carbon everywhere, which means you can make rocky planets everywhere, right? Which means that you have the building blocks for life everywhere in the galaxy, even though you start with 0 of those. And let me repeat this one, the stars had to die to bring you to life. Now our journey is ending. In fact, my clock says 56 minutes. You were scared, right? We were just the middle of March, and then we have to go to December. Because practically, in May, we have the formation of the Milky Way. Then in September, we have the formation of the Sun on the 14th. And when does the Earth form, in your opinion? Very similar, 3 days after in this calendar. The Sun and the Earth are almost coeval. Okay? As you see, from May to September, nothing happens. Why is that? Because you need time for the stars to die, for these elements to spread through the galaxy and bring life everywhere. Okay, now it's a rush. We have to go to December. December 1st, the first oxygen atmosphere develops on Earth. On the 7th, the plankton. On the 20th of December, the plants colonize land. Let me point you to that. We are December 20, we haven't spoken about humans at all, right? Actually, we haven't spoken about another big player, huh? When you think about the history of the Earth, which is not the insects, but the dinosaurs, right? Here it is, dinosaurs. So insects 21st, animals 22nd. The dinosaurs appear on the Earth on the 24th, and they're gone 4 days later, right? They don't last much. So in this cosmic clock, just to tell you again, try to wrap your mind around that, the dinosaurs only lasted 4 days on Earth. Okay? Good. Now, if we want to talk about humans, and that is going to be my last slide, we have not only to go to December, but to move to December 31st. Okay? In order to see the humans, we have to wait 1 hour and a half before midnight. Now, if you thought you were important because you are made of stardust, now you have to think how insignificant you are, right? We are, because we have been around for an hour and a half, right? It's ridiculous. In the whole year, an hour and a half. And now, if I want to go into the next steps, I have to bring in the seconds. So I have 2356 is the last ice age. The cave painting, it's 1 minute, which usually is the beginning of civilization, if you wish. It's 1 minute before midnight. Okay? The alphabet, we have to start to add seconds to our clock. It's 9 seconds to the midnight. We start already the countdown, like 10, 9, 9 the alphabet. Okay? Then we have 4 seconds Pythagoras, Columbus, 1 second before the midnight, and that's it. Time over. Thank you.
Great talk. Thanks very much, Andrea.
Questions?
If you want to ask a question, please use the microphones that are on the sides, and Andrea is happy.
And again, you won't be graded, so it's fine. There's no ABC. Unless you are an NYU student, please. And I can't see people, so I apologize if...
Hi there, Herbert Jelinek. I was wondering if you could just explain a little bit about this uniform distribution with the hot and cold. Like, I understood uniform to be uniform, but you were saying that some parts are warmer than others by, 10 to the minus 5 difference or something. So hence, it isn't really uniform in the first place. So my question is, how did it get non-uniform?
That's
into this little bit in the first place? Thanks.
Yeah. If I ever get my mouse to cooperate. Okay, I have to go back manually. Maybe. Your question is too tough. Okay, there we go. So what happens, it's the only place where quantum mechanics comes into play. I mentioned general relativity, I didn't mention quantum mechanics, and usually when people come to a physics talk, they expect to hear either or, right? It's either general relativity, it's either Einstein or quantum mechanics. As I told you at the beginning, I just do Newton law because I like to do easy stuff. So there we go, our picture here. The problem in quantum mechanics is that you can't make anything too precise. That's called the Heisenberg principle, and that means, and also has to do with the quantum fluctuations. That seems a little bit Avengers jargon, but I tell you it's true. So what happens is that you can't really make something completely uniform in quantum mechanics. To make uniform, you need two things. Think about particles like on a grid. The particles need to be exactly at the crossing of the grid points, and they have to be still. But if you do that, that means you know perfectly the position and the velocity of each of your particles. Think about billiard balls on a billiard. Okay? Let's suppose you want to make uniform. It's very easy. You just put them equally spaced on the pool. The problem is that you cannot do that. That's violating quantum mechanics principles. You cannot know the perfect position and velocity of any particles at the same time. So what's happening here, those are quantum fluctuations. So it's the inability of the nature to create something which is precisely in a place and with a precise velocity. That's where they come from. Is that the answer we're looking for? So practically the universe cannot create something which is uniform.
A great talk, Andrea, thank you. So dark matter, which you've been searching for along with other people for a long time. Is it possible, and I know people ask this question, to throw it out and modify Newton's equation for velocity as the explanation?
Yeah, that's a very good question, and it makes perfect sense to ask it. So because practically what I told you there is dark matter is because I want to stick with my friend Isaac. In principle, if you change this formula in some way, you might fix it. Problem is that if you start to fix it for dark matter, you're going to mess it up for such a number of probes. For example, we don't understand anymore the motion of planets. We don't understand very simple things, especially gravity. It also goes into general relativity. And now I think some of you might have used Google Maps to come here. Google Maps is based on general relativity. The GPS system is based on general relativity. If you try to modify this formula to save Newton, you're going to mess up general relativity. You're going to mess up things like gravitational waves, which have been proved very nicely. So it's very hard to modify gravity. It's like that you have a blanket which is short, right? If as soon as you try to pull it up to cover your shoulders because you want to try to avoid this dark matter, you're going to get frozen feet, okay? And after many years, people have decided that trying to modify this formula, it's a no-go, okay? I have a very nice analogy, if I'm allowed 2 more minutes. The Neptune planet was discovered because people look at the orbit of Uranus and they realize that the orbit was messed up. There must be something that is disturbing it. And they thought, okay, we know what the orbit should be because we know our friend Newton, so we can try to compute what the mess up is. And they told them, the physicists told the astronomers, there must be a planet there. They went and they found it. Okay, beautiful. Now, the other problem was also the orbit of Mercury. The orbit of Mercury is also messed up. It doesn't really follow Newton. And people thought, haha, I know it, Vulcanus, right? I come up with another planet that I can't see because it's always behind Mercury. It turned out that there is no Vulcanus. You have to change the equation. And that's how we went into general relativity. So physicists are not stuck with an idea. We are very happy to modify the equations if it improves. Okay? That's why I don't think we can throw away dark matter by modifying the equation, despite we haven't seen it for 40-something years. I'm starting to lose hope, but I'm tenured. It's fine. Friendly fire.
Hi, thank you very much for this lecture, which gave me this kind of a revelation moment for me and really heartfelt congratulations. Thank you to prove that scientists can actually do slides. So thank you so much for that. But that aside, you mentioned briefly that moment where there's Crab Nebula, and it's like, this is a photo of an explosion.
Yes.
And if we take it 2 years from now, we'll probably see the very exact photo. And that is something that I really can't make my mind, it's where I find my limitation and try to understand. I know it's just because of a matter of scale, But I know if I take a photo of an explosion here, I take it 1 second later and the explosion is gone. And that is actually an explosion. But so is there any moment, is there any data from the past or any kind of optical observation? Is this assisting you in this research, or I'm just a romantic talking about the telescope and you just have to use the computer to use your models? Thank you.
Yeah, very good question. You're not mistaken at all. Now, for the Crab Nebula, if you keep observing, you see tiny differences, very hard. There are other objects, for example, they're called X-ray binaries. Those are black holes that they change daily. So one day they have the light maybe of my laser, and 5 days later it's like a lighthouse pointing to you. They change by orders of magnitude on a daily basis. So we do have plenty of transient objects or strong variability objects. They are studied here at the Center for Astrophysics. The problem is that when you have to deal with the whole universe, things are slow. So there is a beautiful movie that you should all check. It's the motion of the stars around the center of the galaxy. And you see the stars, like planets, dancing around a black spot. Literally a black spot. That's how we know there is a black hole. That's been the Nobel Prize for Physics 2 years ago. Rainer Genzel and Andrea Voigt from Germany and California. Okay, so we see dancing of stars around nothing. That's how we know there's a black hole. So some things move. In my work, no, I'm stuck with pictures, steady pictures.
Hi, I have a question not directly related to the talk, but a little bit meta. So inspired by a talk, for somebody like me who's got a full-time job here in Abu Dhabi, but who's got a bit of an amateur interest in this sort of thing, is there some way we could be involved, knowing the limitation that we can't be there full-time? I don't know if NYU has some way for us to be involved and contribute with our time, if it could be useful.
That's a good question. I think on the tip of my head, on the tip of my tongue, I would say no, we don't have anything like that. There is also a lot to do with liability, so bringing people inside. But there is a lot of opportunities to do summer camps and things like that. For example, our center organized 3 summer camps, 3 actually camps, Astro camps, where people can come and try to do something. So try to work on data. Those are meant mainly, I should say, for high school students but anybody with an interest. We had the photography competition. So there's plenty of option in the outreach part. And I'm happy to give you more pointers if you are interested. I think at the university, it's a bit difficult. But especially if you have interest in astronomy and astrophysics, that's where there is a lot of options for outreach. And now we are going to do this thing back in person. It's going to be much more nicer.
Great. So can we get in touch maybe?
Yeah, sure. Yes, obviously.
Thanks.
Hi, Dr. Andrea. Thank you for the talk. It was very good. Thank you. Just a quick question. What are the prevailing ideas behind dark matter? And what is your preferred idea?
It's a very good question. So there was maybe 10 years ago a candidate for dark matter, which is called WIMP, because we like to give names to particles. And the idea is that we have 4 forces in the universe. We have gravity, electromagnetism, the weak force, and the strong force. Those 2 forces are the ones that keep atoms together. And for example, already in the beginning of the end of the 1800s, we found out that electricity and magnetism are exactly the same thing, right? You can make electricity with a magnet, and you can make a magnetic field with electricity. That's how the dynamo in your bicycle works. Then people have found out that also the weak force gets together with the other 2, okay? And then again, the strong force gets together. So we always try to get this supersymmetric thing, is called supersymmetric theory. The idea is that to take all the forces together, like there is a Uber force, something which is there. And in order to build this framework, a particle comes out. And this particle was a perfect dark matter candidate. And that's what people have tried to look for in the past 30, 35 years. So far, 0, nada, nix, niet, nothing. So maybe it was a very great idea that doesn't work. And maybe we should start looking somewhere else. But that's very difficult, right? Because you have to think out of the box, you have to build new experiments. So there's still hope to find this particle, and there's a lot of people working on that here at NYU Abu Dhabi. And this, if it happens, it's Nobel Prize guarantee. That's why people are not very keen on, because maybe you stop doing it, the guy next to you does it, and he gets a Nobel Prize, you don't. So there is a bit. But I think we are losing hope. And I have other candidates, but I think nature might have made a joke on us, right? It might have put dark matter in a place where we can't find it. There are places where it's very hard to find it. It's a bit difficult to tell you why, but think about that. You are in a parking lot at night, and you've lost your keys. The parking lot is huge, like stadium huge. And there are lampposts in the parking lot. Where are you going to look for the keys? You're going to go from one lamppost to the next one. Because you can't look for it in the dark unless you stumble on it, right? So the first thing you're going to look under the lamppost. And that's what we have done. We look under the lamppost. There's nothing. So now what you have to do is start walking through the whole parking lot and hope to find your keys. Okay? I'm not very optimistic about finding dark matter. Marta might disagree.
Quick question. So, thank you.
Try friendly
So,
microphone.
is dark matter related to a black hole, or yeah?
Well, that's a very good question. And unfortunately, I'm going to tell you no. Dark matter has nothing to do with black holes. Black holes are made, very good question, your parents must be proud. Black holes are made by the same matter we are made of. Okay? There's nothing different about black hole. It's just super small and super hard. Okay? For interesting reasons related to their velocity, dark matter has a very hard time to fall into a black hole. Okay? Dark matter is not much attracted by black hole. The reason is that it's so attracted that when it reaches the black hole, it's so fast that it passes through. So it's very hard to capture dark matter into black hole. Okay? So black holes are made of ordinary matter. Very simple. They're just dead stars. Try to drink again.
Does that mean that if we find dark matter, then we will have found something that moves faster than light?
No. Dark matter, maybe I wasn't clear, and I apologize for that. So think about a pendulum. Have you seen a pendulum?
Yeah.
Right. At the tip, it's at zero velocity, right? When it goes to the center, it's super fast, right? It's the highest velocity. Dark matter is like a pendulum. So dark matter is far away. He sees a black hole, and he says, ooh, I'm going to go into the black hole. But then either he goes straight into the black hole, but if it's just a little bit offset, it will just pass through. Okay? It's like if I throw you a ball, right? If I throw it low, it's very easy for you to catch. If I throw super fast, you will have more trouble. So dark matter is too fast to be captured, but not because it's faster than light. It's just very fast. So some dark matter gets captured, some other doesn't. Mostly of it doesn't.
Again, thank you for a wonderful presentation. Really kind of curious about your thoughts with the launch of the interstellar probe and how that might be able to contribute to future understanding of the universe, and maybe what you're hoping you might be able to gain yourself.
Yeah, which interstellar probe are you referring to? Do you have anything in particular in mind?
We had the major launch from NASA that wound up going out, and you've got your new probe that's now going to be producing, again, massive amounts of new information for us. So I'm curious with your thoughts, right? You're in a competitive business where you're going to be working with your own machinery and whatever else you have. How might that be able to contribute to you, or is that actually going to be detrimental potentially?
Not detrimental at all. I mean, at the end, physics, actually science, it's moved by data, right? The best moment for science is when there is some data that we cannot explain. So that's where we have to stop and start to think. I was telling you before this orbit of Mercury. We couldn't explain it, and then that's one of the reasons why general relativity came out. So, interstellar probes, for example, there are two types. The ones that just sent through the solar system, and those ones are the best proof that Newton is correct, because those probes are moving exactly according to that law. Crazy precision, crazy, right? So they are the best examples of gravity works. Now, there's another set of probes. Those are space satellites. You might have known of the Hubble Space Telescope. Now there's a new one. It's called James Webb Space Telescope. And what they did, instead of putting it in orbit when astronauts can go and fix it, they ship it. So if that's the Earth, that's the sun, they send it on the back, the Lagrangian point, in case you know what it is. And this satellite, it's now, it has unfolded. It has a gigantic mirror. It's an amazing piece of technology, and it's going to give us pictures of galaxies around February so the earliest galaxies, around February, March. And now, if you know how a galaxy looks in February and March, and then you can observe them in October, November, December, you have a better way to connect the dots. So this is going to be extremely useful for us to build numerical models. Okay. JWST, it's there, it's working, and it's supposed to release data a few months.
Hello. Could you explain what it really means to look for dark matter? If we know where it is and that it's there, and what is the limitation? Technology or the detection of it? Thank you.
Yeah, that's a very good question. I told you dark matter doesn't talk with the rest of the matter, doesn't emit electromagnetic radiation. So how can we possibly find it? Dark matter still has a mass, and as a billiard ball, it's going to meet now and then an atom of the ones we're made of. Okay? So the best strategy, there are several strategies, but one, it's not simple at all. It's easy to explain, not simple. What people have built gigantic tanks full of material, xenon, which is a noble gas, and xenon doesn't really interact with anything. What they do now, they cool it down as much as they can, and they wait. The hope is that one dark matter particle of the plenty we have in the galaxy will just go through the tank. It will hit one of the xenon atoms, and so the xenon suddenly will be excited, and we can see the xenon. Okay? It's like, how do you find an invisible man? You find an invisible man, it's fighting with another person, right? If the invisible man is in a corner, you can't see him, right? But if you start fighting with an invisible man, that's the moment when you can catch it. So what we hope is that one of the dark matter particles will go through the xenon in this case. Problem is that this is a very rare event, and so the way to get more is to build bigger and bigger poles of xenon. The other problem is that at a given point, they become so big that are very different to handle, and there is also problems with neutrinos, which I think is slightly too technical for this thing. So people are building larger and larger poles, but they're seeing nothing. And there is a technical limit how big they can be. And when you reach this technical limit, that's where you need to think that maybe you're not looking for the right particle. As I told you before, you're looking under the lamppost. Maybe you have to start looking into the dark, which is much more difficult. I hope no one from Francesco's group was here.
I have a question. So let's just say you find dark matter. What do you do with it then?
That's a very good question. I'm not looking for dark matter, right? I do computer simulations. Let's suppose some of my colleagues find dark matter. That's step number one. Step number two is to prove that is the dark matter, right? You have to prove not only that it's there, but that you have 5 times more than the ordinary matter. So I lost the person who asked the question. Oh, there, thank you, sorry. So what happens is that will be step number one. First would mean that there is a new particle that nobody has predicted, right? Because nobody, let's say dark matter is mainly pushed from galaxy rotation. It doesn't come, not that somebody said in particle physics, oh, there's going to be this dark matter particle. It's more the other way around. So suddenly we have to build a theory for dark matter. That would be super exciting. Second step is to demonstrate that it's exactly the dark matter you're looking for, the one which is 5 times more popular than ordinary matter. So that would be the second step. I would be happy to see the first during my lifetime.
Thank you for a great talk. So I have a question about dark matter, again.
Surprise, surprise.
Yeah, so if dark matter has a mass and it's, how could we explain that dark matter is not at the core of the universe that whatever we're made of? We see that the iron is the most dense one and it's at the core. So how could we explain that dark matter with its mass is not at the core of our universe?
Yeah. To think about the pendulum I was explaining before, the pendulum is oscillating, right? Where does it spend most of its time, a pendulum? I can use another piece of paper, I'm sure. That's within the budget. So you have here ground, you have here the roof, you have here pendulum, which is oscillating this way, right? Where does it spend most of its time? At the extrema. Dark matter does the same. It goes to the center, but when it goes to the center, it's super fast, so it doesn't spend any time at the center. And why you cannot capture at the center? Because in order to capture, let's suppose you're running, right? In order to capture you, I have to literally bump into you. I have to dissipate your velocity. But dark matter is not interacting with anyone. So dark matter is going through. Okay, so that's why it's not at the center. It goes to the center, it just goes away. So if you take a random picture of a pendulum, the chances to find it in the center is very thin. You're mostly going to find there. So that's where dark matter spends most of its time, not in the center of our galaxy. And the reason is that the technical reason is dark matter cannot dissipate its energy. It's a pendulum without friction.
Thank you.
You're welcome. Yeah.
Okay, sorry.
Please.
When you mentioned about the universe breathing, like formation and then explosion, is there some kind of conserved quantity, like matters or something like that, or at least in your model when you do simulation?
Yes, in the universe there are several conserved quantities that are untouchable. One is mass, the other one is energy, and the other ones it's angular momentum. It's the reason why you don't tip while you ride a bicycle. Those quantities are all conserved, and those are inside the recipe. Those are practically, we tell our computer that it has to conserve energy, it has to conserve momentum, and so far, so on. So that's where the law of physics play the effect of the recipe. And now if you think about that, for a computer it's very easy. The computer, what it needs is exactly a recipe. It needs a set of steps to go from A to B. And that's all provided by the law of physics. So yes, quantity are conserved, and this is embedded in the code that we use. Marta, you had a question?
I have a question.
That's a tough one. So the dark matter density is best measured in objects that have the least amount of ordinary matter. So if you look at this galaxy, for example, if you look at the center is very bright. There's a lot of stars. And so in order to, the only thing you can measure with Newton's formula, it's the total mass. Right? Newton's formula is the total mass. So what you need to do to find the dark matter mass or density, if you divide by the volume, is to subtract the visible light. So the best place to look for dark matter are tiny galaxies with very little stars in the center, dwarf galaxies. That's the place which is best constrained in astrophysics, the density of dark matter. Or the best place, actually I wouldn't say it's best constrained, it's the best place to try to constrain the density of dark matter. The best actual measurement, they're all indirect, and I think the solar neighborhood, it's a good place because we have a lot of motion of stars, so we can really reconstruct the 6D motion. So that's a nice place. But even there, we don't know by a factor of 5. So luckily, you don't know whether I am 70 kilos or 350. So it's quite a difference in weight.
Thank you for your presentation was really good. Do you think dark matter abides to the quantum physics, or do you think it has a totally different, set of physics?
Yeah, that's a very good question. The short answer is yes. We believe that everything in the universe abides to quantum physics. Problem is that quantum physics only appears on very small distances. As you have seen in my talk, I'm talking about big things. So in what I do, there is practically no quantum physics. But yes, we believe that dark matter obeys quantum physics. Otherwise, I don't think we would be even able to build a model for it. I can keep talking for hours, but... Thank you very much. Thank you.